Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will see the large signal analysis of this MOS differential amplifier. So just for the continuity, let us quickly recap what we have seen in the previous video. So in the previous video, we have seen the basics of this differential amplifier. And during the discussion, we also learned about the differential and the common mode signal. So we understood that the actual input to this differential amplifier consists of both components. But this ideal differential amplifier only amplifies the differential input signal and it does not respond to these common mode inputs. Then to check the behavior of this differential amplifier to this common mode input signal, we have assumed that this differential input is 0 and only common mode signal is applied to the differential inputs. And considering that, we have seen that when the two MOSFETs are identical and the current source is also ideal, then this differential pair does not respond to this common mode input signal. And therefore, for this common mode input signal, the differential output remains 0. Now then after, qualitatively we understood that how this differential amplifier responds to the differential input signal. And we have seen that as this differential input Vin1 minus Vin2 increases, then the drain current ID1 increases and the drain current ID2 reduces. And hence, this differential output VO1 minus VO2 will become negative. And at one differential input, this entire current ISS will flow through one MOSFET. So in that case, the current through the second MOSFET will become 0 and it will get turned off. And the same thing happens on the other side for the negative values of the Vin1 minus Vin2. That means as the Vin1 minus Vin2 becomes negative, then the output voltage will increase and at one point the current will flow only through a second MOSFET. And in that case, this differential output will become ISS times RD. And here is the change in the drain current with the differential input. So up to this point, we have already discussed in the previous video. Now let us find out at what differential input this entire tail current flows through one particular MOSFET. That means at what differential input this ID1 becomes ISS and this ID2 becomes 0. So let's say at that particular differential input voltage, this ID1 is equal to ISS and this ID2 is around 0. And let's say this gate to source voltage of these two MOSFETs are VGS1 and the VGS2 respectively. Now let's say the voltage at this node is equal to Vs. So if we apply the KVL around this loop, then we can say that this Vin1 minus VGS1 is equal to Vs. Similarly, if we apply the KVL on the second side, then this Vin2 minus VGS2 is equal to Vs. So from this we can say that this Vin1 minus VGS1 is equal to Vin2 minus VGS2. Or in other words, this Vin1 minus Vin2 is equal to VGS1 minus VGS2. So to find the differential input voltage at which this ID1 becomes ISS and this ID2 becomes 0, we need to find the difference between this VGS1 and the VGS2. So now we know that for the MOSFET to be in the on condition, this gate to source voltage should be greater than or equal to VTH. That means at the edge of the conduction where the MOSFET is about to turn off, this VGS is equal to VTH. So we can say that for the second MOSFET M2, this VGS2 will be equal to VTH. That means whenever this ID2 is about to become 0, this VGS2 will be equal to VTH. So now the only thing which we need to find is the voltage VGS1. So we know that in the saturation, the drain current ID can be given by this expression. And here we have neglected the effect of the channel end modulation. So for the MOSFET M1, the drain current ID will become ID1 and this voltage VGS will become VGS1. So if we solve this expression for the VGS, then we will get this VGS1 is equal to square root of 2ID1 divided by mu n times Cox times W by L plus Vth. And whenever this ID1 is equal to ISS, then we can replace this ID1 by the ISS. So at that time, this VGS1 will be equal to square root of 2 times ISS divided by mu n times Cox times W by L plus Vth. So this is the expression of the VGS1 whenever this ID1 is equal to ISS. So now let us put the value of this VGS1 and the VGS2 in this particular expression. So now this V in 1 minus V in 2 or the VGS1 minus VGS2 is equal to square root of 2 times ISS divided by mu n times Cox times W divided by L, which is in fact square root of 2 times V overdrive. Because as we have seen, under the equilibrium, when the differential input is 0 and only common mode input signal is present, then this overdrive voltage VGS minus VTH or this V overdrive can be given by this expression. That means whenever this differential input voltage is equal to root 2 times V overdrive, then this ID1 is equal to ISS and this ID2 is around 0. Similarly, when this differential input voltage is minus root 2 times V overdrive, then the ID2 is equal to ISS and the ID1 is around 0. And here is the input output characteristic of this differential amplifier. So at these two differential input voltages, the differential output voltage will be minus ISS times RD and the plus ISS times RD respectively. That means now at the extreme points we know that how the circuit will behave to the differential inputs. And between these extreme points, qualitatively we know that how the circuit behaves to this differential input. But between these extreme points, we do not know the relationship between this differential input and the differential output, and we do not know the exact shape of this particular curve. So using the large signal analysis, let us find the mathematical relationship between this differential input and the differential output. And let's see how the differential output changes with the differential input. Now finding this relationship between this differential input and the differential output involves a lot of mathematical steps. So if you want to skip this portion and directly want to go to the result, then you can go to this timestamp. Alright, so here this differential output is VO1 minus VO2, where this VO1 is equal to VDD minus this ID1 times RD. Similarly, this VO2 is equal to VDD minus this ID2 times RD. That means VO1 minus VO2 is equal to minus RD times this ID1 minus ID2. That means to find the VO1 minus VO2, first of all we need to find this ID1 minus ID2, and somehow we need to find the relationship between this differential drain current ID1 minus ID2 and the V in 1 minus V in 2, so that we can directly get the relationship between this VO1 minus VO2 and the V in 1 minus V in 2. Or in other words, we directly get the relationship between this differential output and the differential input. So from our earlier discussion so far, we know that this V in 1 minus V in 2 is equal to VGS1 minus VGS2. And we also know that how to write this VGS in terms of the drain current. That means this VGS1 is equal to square root of 2ID1 divided by mu n times Cox times W by L plus Vth. And similarly, we can also write this VGS2. That means this V in 1 minus V in 2 or this VGS1 minus VGS2 can be written like this. And here, if we take this square root of 2 divided by mu n times Cox times W by L as a common, then in the bracket, we are left with square root of ID1 minus square root of ID2. So in this way, we got some relationship between this drain currents and the differential input. But what we actually need is the relationship between this V in 1 minus V in 2 and the drain current ID1 minus ID2. So to get that, let us square on both sides. So after taking the square on both sides, we can write this expression as this V in 1 minus V in 2 whole square, that is equal to 2 divided by this mu n times Cox times W by L plus this ID1 plus ID2 minus 2 times square root of id1 times id2, because as you know, this a plus b whole square can be given as this a square plus 2ab plus b square. So similarly, if we take the square of this bracket, then we will get this id1 plus id2 minus 2 times square root of id1 times id2. And as we know, this id1 plus id2 is equal to ISS. That means we can write this expression as this v in 1 minus v in 2 whole square, that is equal to 2 divided by mu n times Cox times W by L times ISS minus 2 times square root of id1 times id2. So now if we take this term on the left hand side, then we can write this expression as 1 divided by 2 times this mu n times Cox times W divided by L times this v in 1 minus v in 2 whole square minus ISS, that is equal to minus 2 times square root of id1 times id2. And if you multiply all the terms by minus 1, then these two terms will become positive and this term will become negative. So once again, if we take the square on both sides, then we can write this expression as this ISS minus 1 by 2 times mu n times Cox times these v in 1 minus v in 2 whole square, and whole square of this term is equal to 4 times this id1 times id2. So basically we have taken the square on both sides. So now this 4 id1 times id2 can also be written like this, because if you see, then this id1 plus id2 whole square is equal to this id1 square plus 2 id1 times id2 plus id2 square. Similarly, this id1 minus id2 square is equal to this id1 square minus 2 id1 id2 plus id2 square. So if we solve this expression further, then we will left with this 4 id1 times id2. That means we can write this 4 id1 times id2 by this expression. And as we know, this id1 plus id2 is equal to ISS. That means we can write this 4 id1 times id2 as this ISS square minus this id1 minus id2 whole square. So let us replace this 4 id1 times id2 by this expression. That means now we can write this expression as ISS square minus id1 minus id2 whole square, that is equal to this ISS square minus 2 times half times ISS times mu n times Cox times W divided by L times this v in 1 minus v in 2 whole square plus the square of this term, that is equal to 1 by 4 times this mu n times Cox times W divided by L whole square times this v in 1 minus v in 2 raised to 4. So here these two terms will get cancelled out, and if we multiply all the terms by minus 1, then these two terms will become positive and this term will become negative. That means now if we see this expression, then it can be written like this. So now in this expression on the right hand side, if we take this 1 by 4 times this mu n times Cox times W by L whole square times v in 1 minus v in 2 whole square as a common, then in the bracket we are left with this 4 times ISS divided by mu n times Cox times W divided by L minus this v in 1 minus v in 2 whole square. So now if we take the square root on the both sides, then we will get this id1 minus id2, that is equal to this half times mu n times Cox times W by L times V in 1 minus V in 2 times square root of 4 times ISS divided by mu n times Cx times W by L minus V in 1 minus V in 2 whole square. So basically, we got the relationship between this ID1 minus ID2 and the V in 1 minus V in 2. And as we know, this differential output voltage VO1 minus VO2 can be written as minus RD times this ID1 minus ID2. That means if we multiply this entire term by minus RD, then we will get the relationship between this VO1 minus VO2 and the V in 1 minus V in 2. Moreover, we know that this ID1 plus ID2 is equal to ISS. And if we assume that this entire term is equal to K, then this ID1 minus ID2 is equal to K. So if we solve these two expressions, then this ID1 is equal to this ISS divided by 2 plus K by 2, and the ID2 is equal to ISS divided by 2 minus K by 2, where this K is the entire term. So in this way, we can also see how the individual drain current changes with the differential inputs. Alright, so once again, if we come back to this expression, then as V in 1 minus V in 2 increases, then this drain current ID1 minus ID2 will increase, because in this expression, this first term will rise more rapidly compared to the square root term. That means initially, we will get this type of response which we have seen earlier. And if we see the differential output versus the differential input, then the curve will look like this. So here, since the ID1 minus ID2 is multiplied with the minus RD, so we are getting this type of curve. Now as per this equation, beyond certain value of this differential input, this square term will dominate and the differential output will start reducing. And at one point, this differential output will become 0. That means whenever this V in 1 minus V in 2 whole square is equal to this term, then this entire term will become 0. And at that time, this differential output will become 0. But this result is contradictory to our previous result, right? So how is it possible? Well, the thing is, while deriving this expression, we have assumed that both MOSFETs are in the on condition and they are operating in the saturation region. And as we have seen earlier, as the differential input goes beyond these 2 points, then one of the MOSFET will get turned off. Therefore, this equation is valid up to this point where the both MOSFETs are conducting, or in other words, when the differential input is within this range, where this V overdrive can be given by this expression. So this range is the usable range, and in this range, the relationship between the input and output can be given by this expression. And of course, to get the relationship between this output and the input, we need to multiply this expression by the minus RD. Alright, so now let us see how this input-output characteristic changes with this overdrive voltage. So as per this graph, as the overdrive voltage increases, then the curve will spread horizontally, and hence this differential input range over which this circuit works will also increase. Moreover, as the curve spreads horizontally, so the linear region of operation will also extend. So let us understand this point with the change in the couple of parameters. And first of all, let us see how this characteristic changes when the ISS gets doubled. Now we know that these root 2 times V overdrive is the maximum differential input up to which the circuit works properly. So let us denote this root 2 times V overdrive as a VID max. Now when this ISS gets doubled, then the new overdrive voltage will be root 2 times the previous one. Or in other words, the differential input range will get extended by the root 2 times. And since the ISS is doubled, so the curve will also expand vertically. That means by increasing the ISS, the linear range of the operation can be extended. But the downside is that since we are increasing the ISS, so the power consumption of the circuit will also increase. So now let us see the second case where this W by L is doubled. So as per this expression, when the W by L is doubled, then the new overdrive voltage will reduce by the factor of root 2. That means now the curve will shrink horizontally, and since the ISS is same, so vertically the curve will remain same. So basically, with the increase in the W by L ratio or with the reduction in this overdrive voltage, the curve will shrink horizontally, and hence the linear region of operation will also shrink. But on the positive side, since the slope of the curve has increased, so the gain of the circuit will also increase. Because if you see, the slope of this input output characteristic basically represents the gain. That means for the given differential input, how much differential output we can get. That means as the W by L ratio increases, then the linear region reduces, but the gain of the circuit will increase. On the other hand, if we reduce the W by L ratio by the factor of 2, then the new overdrive voltage will be root 2 times the previous one, and hence the curve will expand horizontally. And since the ISS is same, so vertically the curve will remain same. That means now the differential range will increase. But at the same time, now since the slope of the curve has reduced, so the gain of the circuit will also reduce. So in short, by increasing this overdrive voltage, the differential range and the linearity of the circuit can be increased. But at the same time, the gain of the circuit will reduce. That means there is a trade-off between the linearity and the gain. So by controlling this overdrive voltage, we can control all these parameters. Alright, so now in this differential range, because of this square term, the relationship between this input and output is still nonlinear. So if you want to use this differential pair as an amplifier, then the differential input should be very small, so that there is a linear relationship between this differential output and the differential input. So let us find out that range over which we will get the linear relationship. Now in this expression, when this Vin1 minus Vin2 whole square is much less than this term, that is 4 ISS divided by mu times Cux times W divided by L, then this second term can be neglected. So whenever this condition gets satisfied, then we can neglect this term and we can get the linear relationship between the input and the output. So from this we can say that whenever this Vin1 minus Vin2 is much less than 2 times square root of ISS divided by mu times Cux times W divided by L, then we will get the linear relationship. Now we know that this term is nothing but the overdrive voltage, right? So we can say that whenever this differential input Vin1 minus Vin2 is much less than these 2 times the equilibrium overdrive voltage V overdrive, then the relationship between this input and output will become linear. And under this condition, we can say that the differential signal is very small signal and we can use the small signal analysis. So in the next video, for a small differential input signal, we will find out the gain of the differential amplifier using the small signal analysis. But I hope in this video, you understood the large signal analysis of this differential amplifier. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.